That brings us to the last official part of this evening, which is the evening lecture, the traditional evening lecture, which is always a highlight of the first day of the Veldhoven conference. And the speaker will be introduced by Jook Walraven. Jook, may I ask you to the podium?
Thank you very much. It's a real pleasure, and in fact an honor, that I can be here tonight to introduce Alain Aspect as the evening speaker of this great meeting. Alain Aspect is a distinguished director of research at the CNRS, but also a professor of physics at the Institut d'Optique and at the École Polytechnique in Palaiseau. There are three periods in the life of Alain Aspect. He started in quantum optics, where he worked on beautiful experiments looking at single photons, the quantum nature of single photons, and entanglement. And I'm sure that many of you know his famous experiments in which he demonstrated for the first time the violation of Bell inequalities. For that purpose, he also developed single photon sources. And this work really is has been groundwork for an important direction in research now that we call quantum information processing. He worked on this topic till 1985. Then he joined the group of Claude Contenucci at the Collège de France and the ENS in Paris. And there he was associated with the famous work on optical cooling. I mentioned you the blue lattices. I mentioned the blue molasses and the 1D lattices, and not in least place the sub-recoil cooling. That field is important for our present clocks. With cold atoms, time is measured more accurately than ever. And thanks to those achievements, we have precision navigation methods. In the beginning of the 90s, he went back to the Institut d'Optique. And whereas during his first period, he did quantum optics with light, in his present period, most of his work he's doing is quantum optics with matter waves. In Paris, he met the metastable helium atom. He worked with metastable helium at the Institut d'Optique, and he produced the first Bose-Einstein condensate with metastable atoms at the Institut d'Optique. Examples of his work in atom optics are the first demonstration of the Hanbury-Brown twist effect with matter waves, metastable helium. He did it first with bosons, and later together with Wim Wasserman de Vue, the collaboration, with fermions also. And not in least place, also his work on Anderson localization with matter waves. That's the research part. Alain is an enthusiastic teacher. I mentioned his positions. And he is always available to show how great physics is. And therefore we are very delighted that we have here tonight as our evening speaker a person who had many awards, but we like him most because he is very enthusiastic as a young student about physics. Alain, can I give you the word?
Okay, thank you, Jook, for this kind presentation. Thank you, all of you, for being quiet, at least for 1 or 2 minutes. Yes, I'm going to talk about a subject on which I worked many decades ago. And of course, now I like to speak about more recent work, like for instance, Anderson localization of ultra-cold atoms in disordered optical potential, or as York mentioned, quantum atom optics. And I'm not going to talk about that tonight, but I want to advertise. As you see, no, you don't see it, but I should have put the logo of ERC, which means that I have a possibility to fund postdocs. So if some of you are interested in working on Anderson localization of ultra-cold atoms or quantum atom optics, please, you can check with me. I have good European money, which is not yet devaluated, to fund nice postdocs. So tonight I decided when York told me, you know, Alain, it's going to be after the dinner. And I say, will it be a good dinner? And he told me, by Dutch standard, yes, quite good. And I must say that we have a proof that your country can fit well in international standards. So it's at least as good as a similar dinner, for instance, in America. And I asked him, will they have wine? And he told me, yes. And so I decided that I should not talk of too serious and too hard things, that I would rather speak about something which is entertaining and which anyway is fascinating physics, and it's a question of single photons. So of course you recognize this gentleman. This is John Archibald Wheeler, and in case you don't recognize this one, it's the one that usually you see much older, but that's the same. It's Albert Einstein, at the time when he introduced the idea of least quantum. And in case you don't understand everything I'm saying tonight, I recommend that you buy this book. I get royalties on it, and, and everything is explained in all details, and you can find a way to write problems for your students, etc., etc. Okay, so what is it about? It's about the nature of light, and the question of what is light made of has fascinated mankind, humanity, from long ago. In the antiquity, in Egypt, here, in Greece, most of the models of light were particles. But there were, interesting enough, there were two models. In one model, like we see here, the sun is emitting particles with many colors. These flowers are multicolors. It's particles of different colors. This is a very interesting model. But there was another competing model in which it was the eye of the observer which would send particles to the object, and the particle would come again. The idea of a radar, of a LiDAR. This is not a joke. These are the kind of things they were thinking of. Okay, I'm not going to talk more about that, basically because I don't know more. And then we make a big jump. We make a big jump to the Middle Age. In the Middle Age, they were not so much conceptual, but they did something very important. Big improvement in engineering. For instance, they invented looking glasses. Young people don't realize, but when you get at a certain age, you are very happy to be able to put correcting glasses, you know, in front of your eye. And of course, after inventing lenses, they invented telescope, microscope, it was invented in this country, etc. So this was a time of engineering more than concepts. And then the time for concepts came again in the 17th century. Huygens, do I say it correctly? In French we say Huygens. Huygens introduced a model of waves, and his idea was clearly to have an analogy with the riddles on the surface of water. And it was really a fantastic work, but he was not lucky, because there was a big man, Newton, who defended the opposite model, the model that light is made of particles. And the prestige of Newton was so big, and correctly so big, because of the understanding the motion of planets. And also, we must admit, Newton also did beautiful experiments in optics. But with the prestige of Newton, Huygens was defeated. And I must say that I'm unhappy, but maybe as a Frenchman and with people of your country, we could join to complain about British people, okay, together. So the question was more or less settled. Particle is made of particles. Light is made of particles, period. And then, at the beginning of the 19th century, two really great geniuses, Young and Fresnel, established without any doubt the fact that light is wave. And for instance, you can download, if you read French, there are still some people who can read French in this country. There is a long tradition. And if you can download from the website of the Académie des Sciences in Paris, the memoir of Fresnel, it's unbelievable. He has no idea of what kind of wave it is, but all optics is in it. Polarization, interference, diffraction, everything is there. He has understood everything, except that he has no idea of the nature of the wave. And they have to wait for another half of a century until Maxwell establishes without any doubt that light is an electromagnetic wave. And so, as Lord Kelvin said once, by the end of the 19th century, in the 1900s, the question was solved. There was nothing more to discuss. You know, that Lord Kelvin said, physics is completed. Now, the only job that we have is to measure more and more, with more and more decimal places, constants. Well, actually, he was not stupid at all, because he said, everything is understood except two dark clouds. And the first dark cloud was negative result of the Michelson experiment. And the other dark cloud was understanding the behavior of thermal capacity at low temperature. And we know, of course, that the first dark cloud demanded discovery or invention, I don't know how to say, of relativity, and the second one demanded invention of quantum mechanics. So he was not stupid at all. Anyway, you could have the feeling at that time that everything was understood about light. And then the young guy came. And in 1905, he wrote one of several fantastic papers where he introduced the idea that light is made of quanta, Lichtquanten, elementary grains of energy, energy h nu, and momentum p equals h nu divided by c, which was named photon later only. And with this, he made quantitative predictions for the photoelectric effect, and nobody trusted that. It's remarkable that when he was elected in the Prussian Academy of Science in 1911 or 13, well, about within error of 2 years, we still have the report of one of these big German professors writing a report about Einstein. And there is a clear statement. Sometimes Einstein is making bad mistakes, like, for instance, introducing his idea of least quantum. But he has already done so many beautiful things that we are going to forgive him and elect him anyway. Millikan, the great Millikan that you see here, but now they are older. Millikan explicitly says in a review of modern physics paper written 20 years later that you can download, he explicitly says that he embarked into experiments to prove that Einstein was wrong. And after 2 years of hard work, he proved that Einstein's photoelectric effect law was the correct prediction. Okay? And this is a beautiful piece of experimental physics and also a beautiful example of no prejudice. Okay? He embarked with an idea and changed his idea. And finally, you probably know that Einstein got the Nobel Prize explicitly for the photoelectric effect, not for relativity. Okay? So it was really an important thing. And then we know about Compton's experiment, etc. And there is no doubt that light is made of quanta, of photons. But of course, Einstein was absolutely aware that there was a serious problem. Even introducing his ideas of quanta, he knew that you need a wave model to describe interference, polarization, etc., etc. So how to reconcile the particle description with typical wave phenomena? Is light a particle or a wave? Well, the answer to the question, you know it. It's called wave-particle duality. Einstein, again, first, in a fantastic paper, I encourage you to download it, you can find it easily on the web. It's called the Salzburg Conference. There is no reference here, but it's called the Salzburg Conference. In 1909, Einstein gave a conference in Salzburg and gave many reasons to argue that light is both a wave and a particle. And I want just to mention one, and I hope it rings a bell to several of you. He was able to calculate the fluctuations of blackbody radiation in one of these typical, beautiful Einstein reasoning. He takes a vessel, there is a moving wall, there is blackbody radiation on one side, there is particles bouncing on the other side of the wall, and he looks at the fluctuation and poses thermodynamical equilibrium and all that, put constraints, and then he can calculate the fluctuation. And the result is written here, and Einstein correctly interprets the two terms in the following way. The first term, he says, is the term that we would have if it was random particle bouncing on the wall. It's what we call nowadays shot noise. Okay? So it's a noise, a kind of fluctuation you have if light is made of particles. And the second term is a term that you would have if blackbody radiation was made of waves, mutually incoherent, so you have bit notes, and all these randomly distributed bit notes result in this kind of term here. And he said, look, when I do the calculation, I have the sum of the two terms. It means that light is both a wave and a particle. This paper is absolutely fantastic. We, of course, know that Louis de Broglie later, but really later, this is 1909, reversed the idea and say, when I have something which is obviously a particle, like an electron, there is a wave associated with it. So, again, the solution to the question, is it wave or particle? The answer is, it's both. It's both a wave and a particle. But of course, you are not finished with me. That's not the end of the story. Because we can all repeat wave-particle duality, wave-particle duality. The words are easy to say. But how can we represent these words by images? And this is the subject of the rest of the talk. Before embarking into the problems that we have to face when we consider naively, and I think as physicists we must always be naive. So when there are serious problems when we consider naively wave-particle duality, but before embarking to show you these problems, I want first to mention that wave-particle duality, which is at the root of the quantum revolution, has been extremely fruitful. You all know that it is a very successful concept which allowed physicists to understand the structure of matter, its properties, interaction with light. Talking of the structure of matter, if you talk to general public, to your children, or to journalists, I talked to 3 journalists today, okay, and I had to educate them a little bit. You must insist that classical physics cannot render an account of the fact that matter is stable. You all know that. In classical physics, matter is made of positive and negative charges which attract each other and it should collapse. You need quantum mechanics to understand that matter is solid. And of course, you need quantum mechanics to understand chemical bonds, etc., plus several exotic stuff like superfluidity, supraconductivity, Bose-Einstein condensate, plus you need quantum mechanics to invent laser, transistor, integrated circuits. These were not invented by a guy in a garage in California and trying at random. It was invented by the most sophisticated physicists of their time. If you don't master fully quantum mechanics, you don't invent the laser, you don't invent transistor, you don't invent integrated circuits, etc. And so we can say that wave-particle duality is at the root of the information and communication society. But when you consider all these cases, you will easily recognize that it is always quantum mechanics applied to large ensemble. You have zillions of electrons and you describe them with quantum mechanics. You have zillions of photons emitted by the laser, etc., etc. Okay? And then the question is, does this beautiful wave-particle duality model of quantum mechanics, does it works for a single particle? And of course, if you look at textbooks, like for instance, the Feynman textbook, they tell you, yes, it works. Well, except that he's just describing an experiment which had never been done, but this is the way he describes it. So this is how Feynman describes it. He says, okay, we have a source which emits one particle at a time, and I do it as repeatable as I can. Each particle is emitted in the same way as the previous one and the same way as the next one. Then they pass through two holes. Of course, you know that perfectly well. You pass through holes, you have a detector, and when you scan a detector, you find that the rate of detection or probability of detection is modulated like that. And we all know the end of the story, because we observe that when one of the holes is closed, then there is no more modulation, and so the only reasonable interpretation is to say that for each particle, each single particle, we have a wave passing through both holes and more or less guiding the particle towards the bright fringes. Okay, we know the story. Physicists have been fascinated by that since the very beginning of the century. Look, another British gentleman, Taylor, in 1909, he did a fantastic experiment. It was a time where, you know, you had some gentlemen, they were aristocrats and doing a little bit of physics, but they also liked to enjoy life. And this one was a yachtsman. He was a sailor. And so he was looking for an experiment where he could go on a very long sail. So the experiment he did, this is serious. The experiment he did is the following. He put a needle as a lamp, very much attenuated, so much attenuated that in order to observe the diffraction pattern of the needle with a photographic plate, it would take several months. So he sets his device, goes on sailing, comes back, develops a photographic plate, and he observes the pattern. And he makes back-of-the-envelope calculation and say there was only one photon at a time in the apparatus, so one photon has wave-like behavior. And there is a whole series of experiments which more or less are along the similar idea. You take a source, you attenuate the light so much that the average distance between the successive photons is much bigger than the size of the interferometer or whatever device you use, okay? And basically, except for one experiment, all the experiments show wave-like behavior, which means that even when photons are very much separated, you have a wave-like behavior. So, should we consider that the equation is settled and that for sure single particle demonstrate that you can find interference with single particles? Well, when I began to think about this equation in the early 80s, it appeared to me that it was not the case at all for the following reason. Everything we know in modern quantum optics more or less goes back to Glauber. And what Glauber explained us is that when you attenuate a light beam, whatever the initial light beam, after the attenuation, you better describe the beam as a quasi-classical state. And a quasi-classical state has the same behavior as a true classical electromagnetic wave. So for instance, if you look at the average value of the electric field operator in such a quasi-classical state, then the behavior is just like a classical electromagnetic wave. And if you look at the famous G2 correlation function, which is the correlation between intensity, if you write the correct quantum formula, taking into account the fact that you have a quasi-classical state, then the formula is exactly the formula you would write with a classical wave. So actually what Glauber teaches us is that when you attenuate a light beam, don't expect to have something behaving like a single particle. You are going to tell me what is written in all books, except mine, that the photoelectric effect, no, there are several other books who know that. The photoelectric effect, isn't the photoelectric effect a proof that you really need to introduce the idea of single photons separated from each other? And this was the basic reasoning of Einstein when he introduced the least quantum in 1905. Well, from a modern perspective, and this is explained in details in my book, from a modern perspective, you don't need at all to quantize light to understand the photoelectric effect. There is a very clear model which is based on the semi-classical model of light-matter interaction, in which matter is quantized, but light is not. Okay? And for a detector in the quantized matter, we take a very simple model, which is an atom with a ground state and only ionized state. We forget about the intermediate states. They are not relevant for the discussion. Then you say that you have an interaction between this quantum object and the classical wave. You do elementary first-order perturbation theory, Fermi-Golden rule, etc., and you come to the conclusion that ionization only happens if the frequency is larger than the work function divided by the Planck constant, etc., etc. All the features of the photoelectric effect are described by this model. And if you ask me, but where does the quantity h nu or h bar omega comes from? It just comes from the Schrödinger equation, I h bar d over dt. And because you have a sinusoidal wave, you have the h bar omega, which comes naturally in the calculation. So actually, it is not true that the photoelectric effect forces you to accept the idea that you have well-separated photons and stuff like that, okay? So should we blame Einstein? Should we say that he did not deserve the Nobel Prize that he received? The answer is obviously no, because you need to quantize something to understand the photoelectric effect, either light or matter. And in 1905, matter was not quantized. young people who do not know the history, some of them do not know the history, should remember that Bohr introduced the quantization of matter only in 1913. So in 1905, you had to do something. Einstein decided to quantize light. He could have decided to quantize matter. So he was perfectly right. But from a modern perspective, the photoelectric effect doesn't force us to accept the idea that we must describe a weak beam as made of independent photons. So thinking a little more about that, we came to the following idea. Let's suppose here that I pretend that I have a source which emits separated particles, one after the other one, separated photons. For instance, somebody claims that when I attenuated a beam, it's well-separated photons, okay? How can I prove that I will well-separated particles? Well, you can think of a measurement of that type. You put a detector here and a detector there, one detector behind each hole, and you set a coincidence circuit. If there is only one particle will be detected only once, and you will never observe a joint detection. So the rate of coincidence will be 0. This will be a test that you have only one particle at a time. Of course, it's because the idea of a particle is that a single particle cannot be split. But in contrast, if you have a wave, you will have a part of the wave in one hole, a part of the wave in the other hole, and if it behaves like a wave, you will have joint detection. There will be a certain probability to have a joint detection. So this is a serious criterion. Believe it or not, but such an experiment had not been done before we embarked into this work with my PhD student, Philippe Grangier. And if you try to understand why, it's probably because the particle nature is considered as obvious for electron, neutron, atoms, molecule, okay? Nobody would care for checking that it is really particles. Everybody believes that it is particles. And in the case of faint light, well, people did not consider seriously the fact that maybe it was not single particle. They considered that it was obvious when the average distance between photons is large, and they were looking for wave-like effects with attenuated light. But of course, as I have shown you, this is really questionable if you think of attenuated light. So now I'm going to describe in more detail the kind of experiment we did. And as you know, Young slit is nice, but beam splitter is even nicer. So actually, the experiment we considered is the following. We put a beam splitter here, and we put one detector here and one detector there. And the idea is if I have a single photon, then I will have a probability of joint detection exactly equal to 0. In contrast, if I have a wave, the wave is split in two, and there is a certain probability of joint detection, which is different from 0. So we can make a test. We can make an experiment to decide whether it is 0 or not 0. If you are a mathematician, it's very easy to distinguish 0 from non-zero. But if you are an experimental physicist, then there is a equation of error bars, etc. What does it mean? Distinguish 0 from non-zero. Well, fortunately, we were able to derive a relation which would set a very clear limit between the two behavior. Let's suppose that we have a wave which is split in two parts. Probability of joint detection is going to be proportional to the square of the intensity of the light beam, okay? Now, each probability of single detection will be proportional to the intensity of the light beam. And now, we have one of the many Cauchy-Schwarz inequality. For instance, this one, which is spatially trivial, which tells you that the average of the square of the intensity is bigger than or equal to the square of the average. And when you consider the quantities which are on the left of the screen, probability of joint detection, probability of single detection. If you believe in this Cauchy-Schwarz inequality, which applies to the wave description of the experiment, you expect that the probability of joint detection should be bigger than or equal to the product of single probabilities. For people who know the experimental technique of joint detections, it means that the joint detection cannot be less than the rate of accidental coincidences. P1, P2 is the rate of accidental coincidence. So if it is described by a wave, you cannot have alpha less than 1. On the other hand, if you really have a single particle, if you are serious about that, then you think that ideally the probability of joint detection should be 0, and even if there is some noise in the experiment, you can hope that this probability of joint detection is less than P1, P2. So the criterion for a particle-like behavior is to check this quantity and check that it is less than 1. This criterion that we derived at that time is used all the time nowadays with people. You know that single photon source becomes very popular. And when somebody builds a source and claims that it is a single photon source, he measures G2 and he says G2 less than 1 is a proof that I have a single photon source. This is exactly this criterion that we derived. Okay? Okay. Now, first experiment. We had a lot of fun in doing this one. We took a small emitting diode, emitting pulses of a few nanoseconds, and attenuated it with neutral density so much that in the average, there was 10 to the minus 2 photon per pulse. You do the calculation, you know how much energy you have in a pulse, and you put neutral density until the point where you have, by calculation, 10 to the minus 2 photon per pulse. What it means, of course, is that 99% of the time you are going to observe nothing, and 1% of the time you are going to have 1 photon. But it's not the end of the story, because when we did the experiment here for testing whether or not you have joint detection, with these very, very attenuated pulses, what we found is alpha equals to 1 with errors. So it does not at all behave like a single photon. Attenuated light does not behave like a single photon. What is the explanation in terms of the photon? Well, it's quite simple. Attenuated light is described as a Glauber-Quasiclassical state. And if you look for the photon distribution in such a state is not an eigenstate of the number of photons. There is the number of photons is not a good quantum number for that. You have distribution, which is a Poisson law. And in a Poisson law, if you have a certain probability to have 1 photon, you have a probability to have 2 photons, which is basically equal to the probability to have 1 to the square, where there is a factor of 2, but we take care of the factor of 2, okay? So basically, if you have 1 photon, you have a certain probability to have 2. And so there is just enough of pairs in my beam that from time to time, the pair is split. There is 1 photon on one side, 1 photon on the other side, and then I have a certain rate of joint detection. So faint light is definitely not made of single photons. And of course, the next question, do we have means to produce single photon states of light, Fock states, eigenstate of the number of photons? Can we demonstrate experimentally single particle behavior for such states? And the answer is yes, of course. If you want to emit a single photon, it's very simple. Take a single atom, excite it, and wait. And the single atom will emit 1 photon and only 1. The problems at that time, even if young people don't believe it, that nobody knew how to isolate a single atom. We had not developed all these beautiful nanotechnologies, etc., etc. And so at that time, the only kind of source people could consider was classical light source in which you have zillions of atoms emitting. And so you have always a statistical distribution. So the first people to really clearly isolate single photon effects was John Clauser in 1974, who did an experiment with joint detection, which amounted to doing what I described here, but in a quite involved way. But the first people to do a very clear experiment of that kind was Kimball, Dagenais, and Mandel in 1977, I think, yes, or 77. What they did was having an atomic beam, reduce the density in the beam, and so the atomic density in the beam was so weak that by looking with a microscope objective, they had only one atom at a time in the field of view of the microscope objective. And then they observed the fluorescence light emitted by these single atoms. There were one atom coming, the next atom coming, etc. And they could demonstrate a first evidence of a non-classical behavior. That is a behavior which cannot be understood by a classical wave. Okay? What we did was a kind of translation or analogy of Kimball, Dagenais, and Mandel experiment, but rather than isolating single atoms in real space, we isolated single atoms on the time axis. What do I mean? In our source, this is a big, complicated source which had been built for the test of Bell's inequality. And so it's very involved, but basically what this source does is that we have an atomic beam with many atoms which are excited to an upper state, and once they are in the upper state, they have no choice. They must emit two photons in a radiative cascade. So you have a green photon and a violet photon, and the lifetime here is 5 nanoseconds. And in our source, there were many atoms emitting, excited simultaneously and emitting, but the average rate of emission was about 10 to the 7 cascade excited per second. And now, the interval between two photons, the green and the blue, is only 5 nanoseconds. So the average time between two emissions is 100 nanoseconds, and the time between two photons of the same atom is 5 nanoseconds. So if you look what you have on the time axis, you have tac-tac, green, blue, then nothing. Green, blue, nothing. Green, blue, nothing. So the idea was just to isolate that on the time axis to isolate single photons. So the idea was very simple. We detect the first photon of the cascade, and then for the next 5 nanoseconds, we are sure to have one and only one photon emitted. The probability that another atom emits during the same time is small enough that it doesn't change anything to the reasoning. So this is what we did. And immediately, measuring the alpha quantity, the rate of joint coincidence to single coincidence, we found alpha equals 0.2, which is clearly less than 1. So we have demonstrated a very clear anticorrelation, a very clear particle-like behavior. Now I want to describe a modern experiment. You have seen how complicated this source was, several laser, atomic beam, etc., etc. Now, this is a modern way for having single photon emitters. You have a microscope looking at a very dilute sample, and you can, with a confocal microscope, you can observe only one emitter, which is a molecule with a 4-level system. You send a laser pulse on that. The atom is excited to the upper state of the middle transition here, and then one photon is emitted. And then next laser pulse, and you get one photon. It's a little bit disgusting, I must say. It's too simple, but that's the way it is. If you want a review on this kind of modern single photon source, there is a beautiful review paper by Brahim Lounis and Michel Orit. Michel is working in Leiden. I don't know if he's present or not in the room, but if he's here, I will be happy to see him. And there is also another beautiful review paper by Philippe Grangier and Iso Abram. And what I want to describe is an experiment which has been done with one of these beautiful sources. It has been done in collaboration with a group of École Normale de Cachan. And to make a long story short, we have alpha, which is 0.13, which means that it is clearly in the single photon regime. And now, both with the old experiment, Philippe Grangier, or with the modern experiment, we are asking ourselves the question. Now that I am sure that I have one photon and only one here, what happens if I send this single photon in an interferometer, for instance, like this one, Mach-Zener interferometer? What will I observe here? Will the photon go either on one side or the other side, and then I will observe no interference? Or will I have a wave split into parts and recombined? So we did the experiment with Philippe Grangier. This was a beautiful interferometer that was built. It's a Mach-Zener interferometer. It was built specially. And so the difference in the two paths was chosen by pushing or pulling one mirror with a PZT here, okay? And so the experiment was going the following way. We would choose a position, that is to say, choose a path difference, and then we would observe how many counts, and then how many counts here and how many counts in the other output of the interferometer. Then we would move slightly and then count again, move slightly and count again. And this is a result of the measurement. If we wait 0.1 second at each point, basically you see nothing. So we decided to be a little less nervous, to be a little more patient. Rather than waiting 0.1 second, we wait 1 second at each position. And now I hope you can see, I don't know how you see from far, but you begin to see a very clear modulation. Really looks like an interference pattern. And now we were relieved, so we were quiet. We waited for 10 seconds at each position, and now you have a beautiful modulation. You have an interference pattern with a visibility very close to 1. So this sinusoidal variation with a remarkable signal-to-noise ratio shows that we have a wave-like behavior with single photons, because it's the same source as was used to demonstrate that it goes either one side or the other one. Now I show you a similar experiment with a modern device. What we use here is the so-called Fresnel biprism. So you have the light beam which is spread. Half of the beam passes up and goes down. Half the beam goes down and goes up. If there is one and only one photon, it will be detected either in D1 or D2, and we measure the alpha parameter, and we find that it is definitely less than 1. So it's an evidence for the single photon behavior. Now what do? We put a CCD camera here, and we ask the question, do we observe fringes here? Because a Fresnel biprism is, with a normal beam, gives you fringes. So do we observe fringes? Well, I can show you a record of the experiment as it was really done with the single photon device. So I hope that Bill Gates will be reliable. Yes, it is. So I hope you are going to see clearly what happens here. So what you see is the signal on the CCD of the camera, which is here. And the CCD is sensitive enough to detect each single photon. So when a single photon is recorded, you see a bright spot or a red spot. Okay, let's launch the experiment. It's a real signal. And you see single photon arriving. And after a while, you begin to see that they observe on what we are going to call bright fringes. And you see how beautiful the signal is. It's more and more clear that it is a beautiful interference pattern. Okay, and I don't resist to accelerate a little bit and go to the end. Let us go directly to the end. Look how beautiful it is. And this is really done with this source emitting one and only one photon with alpha equals 0.13. Okay, so no doubt, wave-particle duality, it works. What can we say now? Well, we stop for a while and we think. What have we done? In the first experiment, we send a wave packet and we show that it is detected either here or there, and we conclude that there is one and only one particle, and the particle goes either on one side or on the other side. In the second experiment, with the same source, same wave packet, same everything, we send it here, and now we observe an interference pattern. And the only reasonable conclusion is that the stuff, we call it a wave, was split into parts and recombined. So, of course, we have contradictory images. Is it split or not split? Does it go either on one side or on the other side, or does it go on both sides simultaneously? And of course, when you are really in despair, you can always try to go and look into Niels Bohr. So you go into Niels Bohr, and of course, Niels Bohr is never very clear. Well, you know the story. Well, it's a time for story. You know, of course, Niels Bohr was defending a lot complementarity. And among many things, he would claim that clarity and truth were complementary variables. And he made all efforts to only say very true things. Anyway, if you go to Niels Bohr and read Niels Bohr, you find Bohr's complementarity. And you immediately realize that the two experiments are incompatible. You have to choose. Either you use this device or you use that device. There is no way to do two experiments simultaneously. So when you read carefully Bohr, Bohr tells you you cannot speak of a system without speaking of the apparatus which is going to make a measurement. And the apparatus will play a role in the kind of behavior of the system. And so you say, okay, if I understand what he says, it might be that the photon behaves according to the equation. Here, you have a equation. Do you behave like a particle? And then the photon says, of course. And then he behaves like a particle. And then, when you put this system in front of the photon arrives and say, haha, they're not going to fool me. I know there is a Marsen there and Interferometer. And so now it takes the dressing of a wave and behaves like a wave. Well, it's a naive way of understanding the statement of Bohr that it is a measuring apparatus which determines the behavior of the object. But then there is a very smart guy, astute, named John Wheeler, who asks the following question. He says, look, you are not forced to decide between this device and that device when the photon passes a beam splitter. So you keep the two apparatus behind your back. The photon arrives at the beam splitter and says, hey, what is the equation they are going to ask? And Mr. Wheeler says, I'm not going to tell you. Pass first, and then I will decide. That's the idea of Wheeler's delayed choice experiment. So, can we decide the equation after the first beam splitter? For that, we slightly modified our experiment in the following way. And I let you appreciate that you can really tell that this is equivalent to the previous one. With the experiment which is in the upper part of the screen, there is no doubt that if you detect light on the detector D1, it passed up, and if you detect it on D2, it passed down. Nothing happens here at the crossing of the two beams. But of course, in the second experiment, now you have a beam splitter. And so, the only thing you have to do is to introduce or not introduce the beam splitter after the photon passes the first beam splitter. Of course, we are fast, but not that fast. So we are not going to do it by hand. We have some kind of electro-optic device for doing that, but we can do it. So this is the dream of John Archibald Wheeler, who was a theorist. So this is how he's drawing the experiment. You have here the wave packet arriving, the beam splitter, wave packet progressing, and he has not yet decided between this, the equation is which route or that, which is, did you travel along both routes? If you think a little bit seriously about the situation, what you want is that the choice between observing the interferometer or the which path equation, the choice must be space-like separated from the moment when the photon passes the first beam splitter, so that the choice cannot affect the decision of the photon when it passes here. This is how we have implemented the experiment. It's an interferometer in which you have the modern source of single photon, and then the single photon is split in two by a kind of polarization beam splitter. And now we have the two paths, and the distance is 50 meters. So this is a photo to show. We try to compete with CERN, okay? So in CERN, they always show you big pipes. So we show also our pipe, okay? 50 meters is not evacuated, okay? So it's cheap. But you need a pipe anyway because you don't want to have turbulence, okay? If you have turbulence, then you spoil your... Remember, 50-meter separation. It's not so easy to work an interferometer with separation between the beam for 50 meters. And then here, the two beams are recombined, but the polarization are still orthogonal. And so in order to observe an interference, you still have to rotate one polarization. And this, you will do it with an electro-optic modulator. So when there is no voltage on that, this will finish in detector D2, and the path 1 will finish in detector D1. But if we apply a voltage on the electro-optic switch, which is here, then we mix the polarization, and we expect to observe interference. Now, as I told you, we must be sure that the decision to introduce or not introduce a beam splitter must be space-like separated from the input here. And for that, we have a device here which is pompously named quantum random noise generator, which means that it is a phenomenon which is basically quantum, like something like a photoelectric effect or something like that. And we have a noise, and when we are above the noise, it's a 1. When we are below, it's a 0. And this makes the decision either to introduce or not to introduce the beam splitter. And the decision is made, everything is synchronized with the clock, and the decision is made basically when the photon is in the middle of the interferometer here, so after it has traveled 20 meters, okay? So this is how we do the experiment. Then, of course, we have a computer, and we separate the case when the beam splitter is introduced from the case when the beam splitter is not introduced. And also, there is another detail. We have a slight mechanical knob to change the path difference between the two paths. And so we are going to present the data now. So first, I select all the cases when the beam splitter was introduced, and this is the probability of detection here or there as a function of the path difference, and you have a beautiful interference with fringe visibility, not 94%. For people who like beautiful optics, try to think that this is an experiment with separation for 50 meters between the two paths, and in addition, it's absolutely not a monochromatic source. It's very broadband source. So you really have to work close to the 0th path difference, okay? So this is a beautiful achievement. I can say it because, as you easily think, I'm not doing the experiments myself now. It's a PhD students who are doing the experiment. It's a gorgeous experiment, okay? So we observe wave-like behavior when the beam splitter was introduced. And of course, when it is not introduced, what do we observe? Well, we observe that there is no fringe, but more than that, we observe the perfect correlation between the fact that when we block this path, basically there is no count here and all counts are here, and vice versa. When we block this one, almost everything is detected here. This is a which-way parameter, which is a technical parameter to say that it is almost perfect. Okay. So what do we conclude? That here, the photon travels one route or the other, and we can tell which route has been followed by the photon. So what can we conclude? Well, I'm going to let John Wheeler conclude because he has beautiful English, certainly better than mine. So I hope you are going to appreciate. So this is a conclusion of John Wheeler. One decides the photon shall have come by one route or by both routes after it has already done its travel. I think there is not much to add, but I can repeat it another time. One decides, you are here, and you decide that the photon have come by one route or by both routes after the travel is finished. Isn't that beautiful? I think there is no other conclusion to draw from this experiment. Of course, I know that you are happy, you have drunken some wine, but I would not like to spoil the rest of your evening and that you scratch too much your head, so I would like to make some comments which are reassuring. Of course, experimental facts force us to accept this wave-particle duality. It's impossible to reconcile with consistent images coming from our macroscopic world. But first comment, very important, that you must make to all students when they come in your course in quantum mechanics and they begin to ask questions. Or when you have a journalist which tells you, hey, you physicists, you are not serious people. When you like that it is a wave, you say that it is a wave. When you like that it is a particle, you say that it is a particle. You are totally inconsistent. The formalism is totally consistent. When you use the formalism of quantum optics, as it is described in many good textbooks, including the formalism of quantum optics has a single description for both experiments. In the equations, you don't have to choose. Both behaviors are embedded in the formalism. It's only when we insist on having images that then you have to choose. In some case, it's a wave-like image. In other case, it's a particle-like image. I must say that it is the way I work. I have images which are inconsistent, but I know how to manage. And when I'm finished and I say, maybe this situation would be interesting, then I take the formalism, and with the formalism, there is no doubt the formalism is consistent. So this is a good point to notice. Second, I may joke, but Bohr's complementarity is a serious thing. It avoids logical inconsistency. It is true that you cannot do the two experiments simultaneously. But what do we learn by the daily choice experiment? We learn that Bohr's complementarity is certainly more subtle than just the apparatus changing the object. And from this point of view, I would encourage you to avoid invoking the Heisenberg microscope when you teach quantum mechanics. Because the Heisenberg microscope suggests that you have a mechanical action onto the quantum object in order to make the result coming. This is not true. Examples like this one show that it is more subtle than the measuring apparatus just having an action, kind of mechanical action to make the system change its behavior. You have the quantum erasers and all these subtle equations which clearly show that, yes, Bohr complementarity is good, but it's certainly not a simple and naive thing. Now, as a conclusion, something which has crossed all my life, addressing fundamental questions may, at the end of the day, produce unexpected applications. And in that case, the application is quantum cryptography. You have heard of quantum cryptography. The idea is to communicate data, being sure that there is no spy who observes. And to make a long story short, why is single photon very efficient for quantum cryptography? It's efficient because when you have one and only one photon, then the awful spy, the name is Eve, but I refrain from putting a drawing of a beautiful woman because I have been attacked by women who say that it is not nice, okay, because always a bad guy is a woman, okay, so now I have the bad guy with a guy with a mustache and no problem. Anyway, so you have the spy here who is trying to get information. If you have standard wave packets, there are several photons. You can take a little bit of information without being noticed because you have this Poisson distribution. But if you have one and only one photon, if you take the information, you remove that photon. And then you leave a footprint here. And normally, they can check that there is a spy observing on the line. Of course, the real quantum cryptography is much more subtle than that, but you can understand why using single photons is a very big advantage in quantum cryptography. So, just to show that it works, and people with whom we collaborated, Jean-François Roch and Philippe Grangier, are playing and doing quantum communication with single photon at night. And to conclude, I'm old enough that I have seen these two things happening. The Daily Show's experiment is one of the two great quantum mysteries, and here I use the words of Feynman. And thinking about these two great quantum mysteries, unexpected applications came on the way. The first mystery was written in the lectures of physics. We have all read at least some chapters of lecture on physics. And when Feynman describes this single particle experiment, he writes this very strong statement. We are going to examine a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery, and it is a wave-particle duality for a single particle. But 20 years later, in a famous paper, which is a founding paper for quantum computation, Feynman realizes that there is something else, and the something else is entanglement. And if you remember only one thing from this talk, there are really two totally different mysteries in quantum mechanics: single particle wave-particle duality and entanglement for two particles or many particles, the many-body quantum problem, etc. It's totally different in nature, okay? And Feynman realizes this, and he writes about entanglement, an entangled particle, and violation of Bell's inequalities. I have entertained myself always by squeezing the difficulty of quantum mechanics into a smaller and smaller place, so as to get more and more worried about this particular item. It seems to be almost ridiculous that you can squeeze it to a numerical equation that one thing is bigger than another, this Bell's inequality. But there you are, it is bigger than any logical argument can produce, etc. And the beauty of that paper is that after realizing that, immediately Feynman proposes to use this wonderful feature, or this weird feature, to build a quantum computer. So the message is, studying fundamental equations doesn't mean that it's not going to be application. It just needs smart people to realize that when you have a fantastic physical phenomenon, then it's very likely that at one point something good will come out of it. And to finish, I want to present the people who have done the experiment. And I'm going to tell you why I like very much this photo. So you have the people who did the experiment, and in the back seat, the godfathers of the experiment, that is to say Philippe Grangier, who did the experiment in 1985. It was his PhD thesis, and I was a young PhD advisor. So we were in the back seat of this experiment. But what I like in this photo is that this guy is the first PhD student of this one. This one is the first PhD student of this one, and this one is the first PhD student of that one. And so it's a big family, and we all know that physics is a great family. Thank you very much for your attention.
Well, thank you very much for that beautiful talk that shows how mysterious and beautiful our field is. Really fantastic. Well, I'm not going to say much. I'm afraid I'm between you and the party, so I hope you have all enjoyed the evening, the day, and the day is not ended yet. The bar is open. Enjoy.